Today in our video, we are going to be looking at deriving an equation for the charge on a capacitor as a function of time for an RC circuit, particularly during charging. Last week, we left off with this equation that represented how the potential difference varied with time for a charging circuit. All right, and I just want to write this down as a quick reminder to ourselves what we're aiming for. Okay. So the voltage at any time across the capacitor is equal to this EMF. So that voltage or that battery voltage or max voltage is the EMF multiplied by 1 minus E, that Euler's number, to the negative T over RC, and remember that R times C there, that was our time constant tau, which is just our resistance times our capacitance. So I just want to bring that forward because that's actually where we're going to end today. So everything that we're going to do is going to lead up to this. And this is actually going to be a potential as a function of time, but it's going to be very similar and analogous to charge over time, and you'll see that in a little bit. Now I'm going to tell you that while this seems very specific, the steps that I'm going to give you are crucial for your understanding of AP Physics. And so each step that you see written in blue here can be applied to any sort of situation. It isn't necessarily just this one. You can just substitute in variables that are being asked for in your equation. So this method can be used and has already been used over and over and over again. Okay. So what we're going to do today is we're going to start with using Kirchhoff's loop rule. And what I would like you to do is I would like you to do just that. I would like you to use Kirchhoff's loop rule, and you are going to express the potential difference around a closed loop. You can start wherever you want to. I will probably start right here and work my way around clockwise like this. And what you want to do is you want to end up with a differential equation. And when you're looking at making a differential equation, remember a differential equation is d something over d something. And the somethings are always going to be given to you here and here. So you're really looking for dq dt. So whenever you're wanting to write a differential equation, again, it is the charge on the capacitor as a function of time. dq dt is what we're looking for. And you should have a little light bulb in your head right now that says dq dt is also equal to current, right? Is equal to current. So I'm going to ask you to pause your video, take a moment, and I'd like you to use the loop rule to try to write your differential equation using the loop rule that uses the idea or the concept of dq dt. All right, using that loop rule and starting at the point given right here, we are going to use that point right there. Going around the loop clockwise, we have our EMF minus our current, which I'm going to actually just use a lowercase I because that changes over time. You could use an uppercase, it doesn't much matter, times my resistance R, right? And since we're moving in the direction of charge flow, so my I would be in that direction. We're going across the resistor, so we're going downhill in potential, so that's why that number is negative. And then we would subtract minus the voltage over the capacitor, and then that would be equal to 0. Not quite in terms of what we want it to yet, but we're getting closer. We're going to recognize that our current here is going to vary with time, and we would express that as dq dt times R. And then we're actually going to rewrite this voltage, and we're going to rewrite it in terms of the voltage on a capacitor. So you can get back into your equation sheet, and you'll see the voltage across the capacitor is just Q divided by my capacitance, and that's equal to 0. All right, why did I want to do that? The reason why I wanted to rewrite that voltage across the capacitor in terms of Q and C, because that's what this tells me to do right here. right? We need to keep the equation in terms of what you're being asked to write it in terms of. So the things that you can have are your Q's, your T's, your R's, your C's, and then we still have to deal with this guy right here, but we'll deal with that one in just a few. All right, so what we're going to do now is we are going to take this statement. Hopefully we're going to take this statement. Just kidding. On the bus is struggle, friends. Technology is not my friend. All right, we're going to take these two and we're going to forward them to our next page. And what we're going to do with that is our next goal or our next thing that we have to do is we have to separate our variables. And so when we're talking about separating our variables, what we're really doing is we want to separate our Q's and our T's, right? So we need to separate our Q's and our T's. So if we look back to what it is that we're trying to do, here is our Q, here is our T, here is a Q. Everything else are constants. So like our EMF is a constant, our resistance is a constant, our capacitor is a constant. So what we're trying to do is we're trying to separate our variables. It doesn't necessarily matter what we do with our constants, but what we want to do is we want to get all Q's on one side, we want to get all T's on the other side. So what I'm going to ask you to do is just take a minute and kind of fiddle around with that for a moment and see if you can figure out how to get those things separated. Again, we're going to pause and then we'll be back in a moment. What I like to do when separating variables is to get rid of fractions. Since that dq dt is like everywhere, right? It's easier if we get rid of that dt on the bottom and c. So I'm going to multiply the whole thing by both dt and c. That should be a c in there. So when you do that, you'll get your EMF times c times dt minus, and then we have RC dq minus Q times dt is equal to 0. And in doing that, we have a little bit of a more simplified equation to deal with. And we notice that we can move our Q's to our other side. So I'm going to take this term right here, and I'm going to move that to the other side. And in doing that, I'm also going to, JK, I don't want to move that guy to the other side. We want to keep him here. Just kidding. We're going to take our RC dq, we're going to take this guy, and we're going to move it to the other side. My bad. We're going to take that and we're going to move it to the other side. So we're going to have our dq's on one side and our dt's on the other, and then we're going to do some pulling out. So we're going to pull out some of our different variables. Okay, so again, we're rewriting. So then we've got our EMF. We'll move over a little bit. We've got our EMF times our CDT minus Q times DT is equal to, and then we move that term over to the other side, our CDQ. All right, and you're going to notice that we have a DT here and here. We're going to go ahead and pull that out. So then we're going to get DT here. Right? And I'm actually going to change things up a little bit. I'm actually going to pull out a negative dt. And you don't have to, but I think it makes the algebra just a little bit simpler. So again, I'm going to take out a negative dt. So then that's going to be equal to Q minus our EMF times our capacitance. And then we have our RC dq. So I'm just rewriting that. Now notice that I have a Q here on my right-hand side and I have it on my left-hand side, and that's not truly separating our variables. So we're going to divide both sides by our charge minus our EMF times our capacitance. So we'll do that on both sides. And let's clean this up and rewrite, and then we are done with separating our variables. All right, so this is just algebra. dt is equal to RC dq over q minus our EMF times our capacitance. All right, so what I want you to notice is that we have our dt here, and we have a q here, and we have a q here. And then everything else that we see in terms of what is there, those are all variables, right? So, or sorry, they're all constants. So like our R here is a constant, our capacitance here is a constant, here's our constant EMF, and then here's our constant capacitance. So our variables are separated. Our Q's on one side and our T is on the other. Okay, so then we're gonna go ahead and head on to our next step. So I'm gonna take this image and I'm gonna paste it into our next step, which is step 3, which is going to be to determine the limits of integration and integrate both sides of the equation. So our next thing that we really need to do is to figure out what we need to integrate. So again, we're trying to find an equation for how charge varies with time. And so if we look at our limits when we integrate, if I can find what I'm looking for here, when we integrate, there we go. We are going to integrate this with our limits of time 0 to some time t during our charging, right? So we're charging that. And then over here, again, we are going to have 0 charge on our capacitor to begin with. And then we are looking for charge as a function of time. So we really want to know what is the value of the charge at a given time. So this little guy here is a t. I feel like it won't do that well for me, so I'm going to try again. So then what we're going to do, so that's charge as a function of time. There we go. Okay, so we've determined our limits of integration. We're going from 0 on both of those to t. And then for the charge side, we're going 0 to the charge at that given time. And so now your job is going to be to use those limits to integrate both sides of the equation. I'm going to tell you right now, I would suggest using a table, especially for that right-hand side. Left-hand side, super easy, cheesy, breezy, beautiful cover girl, but you're going to need to use a table, and specifically you can use your table that is on your AP equation sheet. So if you don't have that out already, get that out, and I'd like you to try to do that integration solo mission. Do not evaluate the function yet, so just do that integration. Okay, so I like to simplify before I try to integrate, and so I'm going to pull out my constants. So I'll pull out my RC, I'm going to pull out my negative here. So when I do that, I end up with the function that is shown here. So literally I'm just pulling out my constants, my negative here and my RC here. Okay, this guy over here is super simple. That'll just end up being t, right? So I'm taking the integral of that. This one, on the other hand, is a little bit more complicated, and if we really pay attention, that this right here is going to be our constant, right? So we have this guy here and this guy here, that's our constant, whereas this is our variable and this is our variable. So if you look on your green equation sheet, look at that calculus column on those equations, and you're going to see this relationship, which is exactly the format that we have, right? We have this is our variable and this is our variable, and then we have our constant here. So we're going to use that same integral. So we don't actually have to do that integration by parts. We just take it, which is kind of nice. I'll tell you now that the AP equation, they're not going to make you integrate by parts. They're going to expect you to be able to look at a table and figure that out. They're not testing your calculus skills, but you do need to use the calculus in order to be able to solve this. Okay, so then our next step is going to be to simply apply that. So again, we said that left-hand side there is just going to be our t. I kept that negative. I just pulled that down. And then we're going to evaluate that here from 0 to t. And then over here on the right-hand side, again, we have our RC, and then our resistance times our capacitance, and then our natural log, and that is an absolute value. And then our variable, again, is Q, and then our constant was our EMF times our capacitance, and we're going to evaluate that function. So this line here is the evaluate, and we're going to evaluate that from 0 to our Q, our charge at any given time. All right, so then our next step is going to be to evaluate the function with those limits. All right, so let me grab this and pull that forward. So what we're going to be doing is we are now going to evaluate the functions with the limits. So essentially, we're just going to be plugging in those values. Remember, you always take final minus initial. So we're going to take final minus initial. So go ahead, pause the video, take a moment, and do that. Okay, evaluating those functions with limits, super easy on the left-hand side. The right-hand side gets a little trickier since we have to substitute in at this place for Q, but it's not too bad. So here we go. We substitute in 14, 0, and on the left-hand side, that'll just leave us with a negative t. I went ahead and pulled RC out because that just makes that a little bit simpler and a little bit cleaner. And so then we substitute in always final minus initial, so we substitute in our Q as a function of time. So our natural log, and then we have those absolute value bars, Q, so charge is a function of time minus our constants of our epsilon, or our EMF, times our capacitance, and then there's another absolute value bar. So that was substituting in this guy right here, minus then again our natural log when we substitute 0 in for Q right here, and we'll get just a negative epsilon, or EMF times our capacitance. I like to use a property of natural logs to simplify what we're looking at, because I think it just makes it quite a bit more simple. And when we do that, that identity of natural logs, the natural log of A minus the natural log of B is equal to the natural log of A divided by B. So you can essentially see that we have our A is here, this is our B, and we're just rewriting this statement in terms of that division, the natural log of A divided by the natural log of B. Also notice that I just divided the RC to the other side. There's no real reason, just I was trying to clean up that right-hand side a little bit. Okay, so we just finished our step 4. Is that our step 4? Woo, only one more step to go. So we've done our step 4, and we're going to take this function right here, and we are going to simplify it. So that's our 5th and final step. So we're going to take that and simplify it. So again, remember the goal is to get a function of how charge varies with time. So essentially, we want to rearrange this whole equation and solve for that, because that's the holy grail. That's what we're trying to do. So right now our calculus is over, our physics is over, it is just algebra now. All right, so I'd like you to take a few minutes, pause the video, work that algebra, and I'll be back with you in just a moment. All right, so here we go to finish this out. We really need to get rid of that natural log, right? And so we'll take both sides, e to the, and we will get an expression that looks like this. At this point, you should start seeing some things that look familiar. And then we just algebra that out and rearrange and start solving for Q, right? And when we do that, we get Q, the function of time, or charge as a function of time all by itself. And now on this side of the equation, I'm just going to pull out that EMF times the capacitance, since it appears in both terms here. And when I do that, I'm going to rearrange it a little bit, and you're going to notice something. You're going to notice this that looks so much like that function that we started talking about at the beginning of this video 20 minutes ago. So we have charge as a function of time, and then we have our epsilon times our capacitance. Notice that is going to be our Q max. So if you go back and you look at your relationships between capacitance, charge, and potential, that is going to be our maximum charge on the capacitor. And we get this 1 minus e to the negative time. There's our variable time, right? And then we have that RC, right? So here is that time constant RC there, which is an important one to notice as well. So if we look at like what are we really trying to find, what was our goal? Well, our goal was this, right? This is what we were trying to find the whole time. We wanted to know how the charge varied with time on a capacitor, right? And it increases at a decreasing rate, and it asymptotes to that value of Q max. How does this relate to the lab that we just did? Well, if you use that same idea, that capacitance is the definition of the charge per potential difference. So the voltage at any time can be rewritten in terms of that capacitance. So if we do that, it looks something like this, which is exactly what we found in our lab, or exactly the equation that we used in our lab. Okay, so big recap, big ideas of what we wanted to do is we wanted to find a charge as a function of time on a capacitor, and we did 5 different things to make that happen. So those 5 things that we did, remember, are we started by writing the differential equation in terms of the variables that we wanted. Remember, d something is always d something, or like differential equation is always d something over d something, and that is given to you in terms of charge and time. We recognize current is charge per time, or the dq dt. Then we separate our variables, getting our q's and our t's on different sides of the equation, so we end up with t's on one side and q's on the other. At that point, we are ready to integrate, so we have to set our limits of integration. That top limit here is going to be that function, because that's what we want to figure out. How does charge vary with time? And so then we integrate, we use a table to do so, right? To make that integration a little simpler. Notice we have how we're evaluating those integrals. And then after we have integrated those functions, we got to put those values back in, or we evaluate the functions with the limits that you created. And then we just do some algebra and start rearranging until we get to our final product, which is an equation of how charge varies with time. The biggest ideas that you need to be able to recognize is how to write a differential equation that di, or that current is dq dt. We need to understand that those variables need to be separated, and that we need to integrate with appropriate limits. Those are kind of your big ideas for this. I will post this, and I hope this finds you well, and talk to you all soon.